Okay, so it's 9 o'clock, so we can get started. I would like to say a big welcome everyone here on site in the room and everyone who is with us via the Teams. My name is János Harmatos from Ericsson Research Hungary, and I'm representing the Deterministic 6G project here as a project coordinator. And after 2 years and 9 months, Deterministic 6G project is approaching its finish line. So we would like to take this opportunity to share some key achievements, key results from the project. But in the beginning, let me share some practical details regarding the day. First of all, let's take a quick look on the agenda. We will start with a few introductory presentations, followed by a keynote on 6G in the first morning session. And we will continue with a deep dive into different technical areas of the project in the second session, second morning session. And after lunch, we will continue this journey with another technical areas. And for the on-site audience, we will have a special session in the afternoon where we can, or we intend to showcase a few demos where we want to demonstrate the different features developed in the project in a practical way. For each technical presentation, we are planning a short Q&A part. For the online participants, please use the chat if you have any questions, and we can tell your question to the presenter. If there will be not enough time, then we will answer your question via the chat. And some practical info for the on-site audience. So if you need a Wi-Fi password, please connect to this guest Wi-Fi and then send an approval request to one of the Ericsson colleague, and we will approve it. And yeah, one more important thing, the door will be locked, and an Ericsson card is needed for you, but we have a, let me say, golden card. And there is a red chair just on the door, and there is a hanging card on the chair. So you can use that card if you need to go out and go in. So that's it, I guess. And so in the beginning, I would like to give a very short introductory presentation for the project. So in Deterministic 6G, we have considered such use cases which leverage this cyber-physical continuum paradigm. And the essence of this cyber-physical continuum is that there is a physical world with equipment, actuator, sensor, and there is a digital domain with the representation of the physical world, or with some virtualized functions which controls different entities in the physical world. The illustrative use cases for the cyber-physical continuum could be, and these are investigated in the project, the smart manufacturing, smart agriculture, this wearable robotics, occupational exoskeleton, and extended reality. And the commonality of these use cases is that there is a very strong relationship between the physical and the digital world, and there is a very strong dependency between these two domains. And it means that if we want to ensure and guarantee the required service performance for this application, then we need to have or need to provide time-aware traffic handling in the underlying communication and compute domain. And if we see the legacy wired solution, then we can see that there's a very well established standardized set of solutions. So, for example, IEEE is standardizing the time-sensitive networking, the TSM, for layer 2 time-critical communication. And IETF is working on the layer 3 solution. This is the deterministic networking. So we have a quite solid feature set for deterministic communication in a wired domain. And if we see the 3GPP activities, then we can say that from release 15, an activity has been started concentrating on the integration of the 5G and the TSN system. And together with the ultra-reliable low-latency features, we can say that there is a solution for low-latency communication. So we can ask, what's the problem there? So the issue is that in itself, low-latency communication is not deterministic and not time-aware communication. And if we zoom into the different domains and we consider the characteristics of the domain, then we can see that instead of stable latency and static latency characteristics, the wireless network has rather stochastic latency characteristics. And even in the case of low latency communication, we need to consider a very high packet delay variation. And to some extent, this is true for the compute domain. So due to the shared resource paradigm, we are facing some timing uncertainties in the task execution in the compute domain and uncertainties in the traffic handling of the virtualized networking of a compute node or host. We could say that, okay, let's try to eliminate these stochastic characteristics, and let's try to guarantee a real deterministic packet delivery. But in the beginning of the project, we have concluded that this is not really possible. So the complete elimination of these stochastic characteristics is not possible. So that's why some level of uncertainty remains in the network. And that's why in the project, we use two approaches. The first approach is to try to mitigate this kind of stochastic characteristics on one hand, and on the other hand, try to make them predictable. So let's try to characterize this kind of behavior and try to predict these characteristics. So this is the first approach. The second approach is try to live with these together with these stochastic characteristics and try to mitigate these stochastic characteristics into the end-to-end system design and combination, system design and configuration. And our main intention was to use these two approaches in a combined way in the project. Okay, so the main objective of Deterministic 6G project is to develop essential architectural principles and different type of new conceptual solution for realizing this end-to-end dependable time-critical communication provided by the 6G ecosystem. As I mentioned, we implemented these two approaches in an integrated, combined way, and our intention was to cover the entire end-to-end loop, considering the communication, wireless and legacy TSN communication domains, and the compute domain. And I would like to say some words about the various technical areas of the project. During the day, you will get much detailed information and results about what we have achieved considering these areas. So we have started with a quite extensive use case investigation. Our intention was to describe the key KPIs, the KPIs and the key characteristics of these use cases. And together with this, we have also defined a so-called dependable service design, service description framework, where the application is able to specify its requirements for the underlying communication and compute domain in a very detailed way. And in addition, the application is able to specify its capability to adapt to the different changes in the underlying domains. The second area focuses on the enhancements of the 6G system. Here, our intention was to do some kind of investigations regarding latency characterization and prediction of the 6G system, but we have developed various packet delay correction methods in order to support the time-aware communication. The third area is focusing on the second approach, concentrating on the wireless-aware or wireless-friendly enhancements of legacy TSN and NetNet system to make them capable to integrate, seamlessly integrate these stochastic characteristics of the wireless and the compute system into the end-to-end system design. We developed several features for the compute domain, especially for the virtualized networking part. And because we are talking about time-critical communication, time synchronization is an essential building block. So we have done some investigations regarding time synchronization, focusing on the reliability of time synchronization. And we had a solid security track. On one hand here, we investigated architectural features, but we also developed cyber attack detection and mitigation methodology tailored to time-critical communication and attacks to time synchronization. And because we have developed the different concepts, it was really interesting to, expectation to validate these concepts. So that's why we have developed the simulation framework for covering the 5G and the TSN domain, and to some extent the compute domain as well. And we have performed an extensive validation of the different concepts. And here, just briefly, I would like to show the deterministic 6G projects in numbers. So we have prepared a lot of deliverables plus journal and conference paper. We had a quite solid contribution to different standardization fora, and I think that we could be proud that we have, based on the results of the project, we could initiate a new standardization activity, a new standardization project in IEEE, focusing on the extension of the legacy TSN standards to consider the characteristics of the wireless system. And we had several keynotes, workshops, special sessions on various conferences, and the project has released different kind of open source software packages, like the simulator framework, various models, data sets, network delay emulator, the software for the security solution, and the latency measurement framework to characterize the latency in 6G networks. And I think, yeah, we could be proud of these results. But at the end, I would like to stop for a moment and, yeah, let me show another slide. The title of this slide is Deterministic in Pictures, because if we take these results on the previous slide, that we should consider that behind the results there are people, I guess. And I'm pretty sure that in deterministic 6G, beside the technical solution, we could establish a really friendly and productive working environment. And I think that this nice working environment was a really major factor to achieve these results. So we will continue with the technical presentation, but I think during this day we can show something from the spirit of deterministic 6G as well. And now I would like to give the floor to Professor James Gross from KTH, who is the technical manager of deterministic 6G. So, James.
Okay. Thank you, Janos. So, good morning, everyone. Here from Tista, from beautiful Stockholm. And now I have the pleasure to give you a couple more details regarding, on the one hand side, the motivation of the project, and then the circumstances at the beginning of the project, and then also how certain technical work streams actually panned out, and what we found. And I thought I put the whole presentation under a motto. It's a little bit, let's say, controversial, but it's early in the morning for some of you, I guess so. To wake you up, emulate a wire or predict and adapt, right? So that is what I would like to put the presentation under. Okay, so let's look a little bit at the background, the technical motivation of deterministic 6G. And here I would like to come back to a story that is intriguing the communications and networking community, essentially already for 20 years. And the question, the fundamental question is, what is there beyond human-based communications, right? And will network infrastructures be capable of luring and pulling in other application types into network infrastructures? And this is something, right, that goes under the synonym of the cyber-physical system. And 20 years ago, roughly, people started to work on scenarios where we were capturing states from reality, but the goal was always to push these states then back somehow to a server through a network infrastructure, and then do something with this type of information. Now, it's not hard to imagine a scenario where there's a higher utility from such an approach, and this is where you just close the loop, right? So instead of just reading kind of like sensor information, and then processing that kind of like offline, right? Why don't we put in actuators, right? Close the loop and then try to manipulate reality. And behind this seemingly somewhat harmless figures and so on and so forth stands a whole array of applications that we all can subsumize under the cyber-physical systems concept. And the key thing here is that when we do that, when we start to close the loop, when we try to manipulate reality, in an automated fashion, then these notions of dependability all come in. Then the focus swings towards latency and reliability, and this over the entire loop. So due to this realization, right, which is already around for 20, 15 years, we see today, or 3-4 years ago when we started the project, quite a diverse, let's say, set of technologies in cyber-physical networking that people have been evolving, that also commercially were brought to the market. And this was essentially all developed during the 2010s. And these are, let's call it technological islands like TSN.NET, 5G URLLC, OPC UA, and edge computing. Now, these technologies all have something in common. On the one hand side, they are inspired for this need for lower latencies, higher reliabilities in networks. But on the other hand, a lot of them also have the feature that they're trying to eliminate impacts that stochastically are existing in network infrastructures in different ways, by providing more redundancy, by modifying topology, and so on and so forth. And one can also say that most of these technologies have been somewhat independently evolving over time. Now, they're all inspired from the same root, but they have been taken up from different communities at different times and then pushed forward. Okay, so now looking at these technological islands, looking at their principal approach, now let's have a look at what we're trying to pull off in 6G, right? And in 6G, we want to extend the story that we were already evolving in 5G, where it was mostly leaning towards trying to support automation scenarios, right, in well-defined environments. And we would like to open this up towards what we call the cyber-physical continuum. This is something that János has been already mentioning. And think of the cyber-physical continuum essentially as a huge amount of these closed-loop reality processing applications that are running all over in a certain spatial environment. So this is a snapshot of Stockholm and drawing of Stockholm, right? And what we're envisioning in 10 years is everyone's running around with augmented reality glasses, and there's a ton of autonomous cars that are driving around, and they're all supported by the network. Right? They're all offloading reality information into the network. And this is, I always think of this a little bit like, right, every individual cyber-physical systems loop is like a flashlight, right, that from the network infrastructure is kind of like capturing a certain aspect of reality. And the more of these flashlights you have, then you start to see all of a sudden at the back end, you start to aggregate a more and more complete view of what's happening in reality, right, if you mesh this together, right? So we're moving in this direction, right? So we need much more scale of these systems, much more integration. And the key thing here is always the emphasis is on the loop performance. And loop performance is not a single hop anymore. Loop performance is everything from the RAN through the core to the compute and the whole thing back, right? That is the KPI, so to say, of these systems, right? Of these cyber-physical continuum. Okay, so in order to enable that, then what do we need from 6G in terms of cyber-physical networking capabilities? A couple of these islands are already there, but we think we need more, right? And this more can be summarized under the concepts of convergence and scalability. On the one hand, we want to connect these islands, and that is where the convergence comes in. And on the other hand, we have to do that in a scalable fashion, right? So if you want to have all these cyber-physical systems that are running automatically over a larger spatial area, an unstructured spatial area, you need a lot of automation support, right? To plug them into the network, to run them, to deal with errors, and so on and so forth. And or unforeseen states. And this is not only in the application domain, this is also unforeseen behavior in the network infrastructure itself. Okay. So that's what we want, convergence and scalability, and that was the starting point of deterministic 6G. So then, in deterministic 6G, the first thing that we did, taking the name deterministic communications into account, is we start to look into definitions. And this is something that is known in some of the communities, but this was important for the project. So now, deterministic packet delivery is providing the right packet at the right point in time. And it's no problem if you have somewhat variations, as long as the right point in time is always kind of like behind your variations. But what is also important in deterministic communications, it's not only the right packet at the right point in time, but you actually know upfront how a certain element is going to behave. And you know that with certainty. So you have something that is called plannable, a plannable aspect of the communication or of the response of your infrastructure. Now, if we take the example of 5G, right? In 5G, we of course know, right, there's a wireless system, at least right in the front end, and we have certain variations of the latency, right? Now we introduced URLLC. what URLC is basically doing is that it reduces this difference, the variations in the system between the minimum and the maximum, such that we're looking at very compressed packet delay variations. But of course, you can ask the question on the one hand side, still in comparison to other systems, these packet delay variations are significant. On the other hand, to which extent are these wireless systems really plannable, that you have absolute certainty about how these packet delay variations exactly are going to pan out? Okay, and that, if we now wrap that a little bit into a different frame, boils down then, that if you review strict determinism, you come with certain characteristics, and it's just becoming clear that if you observe the entire loop, that these cyber-physical systems in the cyber-physical continuum will have to cover, that many of these elements have stochastic variations, where it is inherently difficult to pull off this bounded behavior and the plannable behavior. So what to do? And this is then where the approach of deterministic 6G really comes in, where the central statement is, let's instead of eradicating stochastic behavior as much as we can at any price, we try to embrace stochastic elements, but try to make them predictable, to get this feature of plannable service and then manage them in order to fulfill certain requirements that are coming from the applications, but harmonize that at runtime of the system continuously, to pull off what we would call dependable communication for time-critical services. So, illustrating that in a somewhat simplified fashion, we have here the varying wireless link, or a varying service from a compute element, whatever you want to interpret into this, and so to say, current state-of-the-art approaches are trying to do this. They're trying to insert a floor into the system at potentially a relatively high price. Instead of doing that, the idea of deterministic 6G is to say, well, why don't we chop time up into certain time intervals, and in advance of these time intervals, try to figure out how these elements are going to be behaving, so predicting this behavior, and then harmonize this varying behavior, these varying steps, with whatever the application needs or can deliver in terms of flexibility towards the underlying network infrastructure. So, and that's where the question comes up. Shall we emulate a wire, or shall we predict and adapt? Okay, in deterministic 6G, this then boiled down to a definition of dependable communications, where we say dependable communications is characterized by quantitatively ascertain the delivery or required service performance for the communication that has been agreed. So you need to be quantitatively able to characterize your individual elements and then also concatenations of these elements. And you do that up front, and harmonize that, therefore, with the corresponding applications. And if the applications require something that the infrastructure cannot provide for whatever reason, then there must be a certain process of graceful degradation. Okay, now that boils down to a different couple of steps in the architecture. We're going to see much more about that later in the afternoon. But essentially, you always need to run through a loop where you're first identifying service levels together with the applications. Then you're monitoring and predicting the service delivery and the future service that you're anticipating. During this business, you're also automating service assurance, so what you had been agreeing on. And then you give feedback to the application domain, and you go into this loop again to renegotiate and then kind of like execute the system. Okay, so that's, so to say, from the approach, the direction that deterministic 6G has been taking. Now let's look at what we actually were capable of getting done. And within 12 remaining minutes, I can only jump through a couple of these results. A lot more of these details are going to be shown later in the or during the course of the day in the presentations. We also prepared a couple of really nice demos here. And so I really hope that you will enjoy much more technical depth than over the next couple of hours. So the first question in this context is, what is actually a predictable system? And this is really interesting because you would think, 3-4 years ago, at least the way I perceived it, everyone was talking about predictability. We need predictability from systems. But if you look into literature and you try to nail this down really precisely, it was very hard to find actually how you would define predictability. So we were not very happy with this. And so what we engaged in was a theoretical work to explore how we could come up with information theoretic measures for predictability in systems. And the proposal that we made, and this is inspired actually by work in atmospheric sciences, so we had to borrow mathematical concepts from different fields that were dealing with these questions already much earlier. So the concept that we came up with was to say, okay, well, if you have a stochastic system with a KPI reaction, and the KPI reaction is given here by the random variable z, and you're conditioning now the probability of this KPI on a certain observation. Is there then a difference in the future behavior of the system if you know this information or if you don't? All right, so to say, in mathematical speech, we're looking at the transient conditional behavior versus a stationary behavior of the system. Okay, and then, and this is given here by the blue and by the green, yellow curve. The yellow curve is the conditioned one. The blue one is kind of like the steady state behavior of the system. The definitions that we then borrowed came up with the statement that the system on the left-hand side, if there's no difference, regardless if you know something or not, with respect to the behavior of the system, the anticipated, then the system is defined unpredictable. And that's to some extent controversial. Whereas in the other case, we call the system predictable. And note the emphasis is here mostly on what do we know about the system? What's the value of the knowledge that we have, the system that makes it either unpredictable or predictable? Now, why is this any good? And yes, this is actually very, very interesting. So coming from these fundamental definitions, we derived a certain metric that measures predictability. And we could pull off certain results. And these results are fundamental for investigating the design between observability and predictability in systems. So for example, we found that we can characterize in concatenations of predictable systems the total predictability of the sum of these elements as they're interacting. And there are certain bounds that are valid and that are helpful in the characterization of the overall predictability. We also found when you have such a concatenation, you do not need to worry about every individual link. There are certain links or certain elements that you have to focus on when it comes to observability because they're dominating the predictability of the system. And this gives a very good, let's say, mathematical foundation for further system design questions. Of course, this is always math and system modeling, so it's not capturing everything that exactly happens in reality, but it's a good framework how to think about systems in the future. Good. Switching gears, right? We're not only interested in theoretical bounds around predictability, we're also interested in actually how can we predict something on given wireless systems or also given compute elements. Now, in the literature, it's well known that, for example, when you're looking at the latency behavior of wireless systems, these latency distributions, histograms, are oftentimes heavy-tailed. And that's a challenge when it comes to predicting then the latency of these systems, because you need to deal with special, let's say, machine learning models for which then you also, if you're not carefully designing them, you need to collect actually a lot of information, a lot of training data until you capture also a precise behavior further down in the latency, in the latency spectrum. Okay, and one approach that we followed here was to take extreme value theory, which is mathematical theory about the tail behavior of certain random variables, weave that together with so-called mixture models, and then study their performance when it comes to synthetically generated data of latency of systems, of communication systems, and then also study this behavior when it comes to real measurements And a central result here, and this is shown on the right-hand side, is that these modified mixture models, where we then add also these heavy-tailed distributions in, are much faster, capable of characterizing relatively precisely the tail. And this is now here a plot on the right-hand side, where it's about the tail probability on the y-axis and the link delay on the x-axis. And this is based on real measurements from 5G systems. So this is a very good result to build on top for future predictable systems when you're actually trying to implement that in reality. Okay, then moving forward, so what can we do with these predictions? One central aspect of deterministic 6G has been to look into TSN and the TSN integration with 5G. Now TSN basically, for TSN in general, for the end-to-end scheduling in TSN, so-called bridge delays are a central concept, the port-to-port delay of a bridge, because this determines essentially how tightly you can construct these end-to-end schedules. And of course, in a wired system, in an Ethernet-based system, these port-to-port delays in a corresponding bridge are extremely small. Now, somehow you need to extend that to the wireless domain. If you just take these concepts from TSN and you extend them the way they are defined for the wired domain, you come with arbitrarily large reservations of time blocks in an end-to-end scheduling that results from the packet delay violation that you would see in wireless systems. So essentially you're trying to capture 100% of the probabilistic mass of a packet delay violation, of a packet delay distribution, and then you map that into reservation times in the TSN domain for a particular hop. Now if you take into account that you actually have knowledge up front about this stochastic element, we showed in the project that you can actually construct these TSN schedules end-to-end in a much more efficient way, embracing the stochastic variations, but knowing quantitatively how these variations are playing out. And then you could also get rid of a couple other constraints that are typically upheld in the TSN domain when it comes to this end-to-end scheduling, leading to a much higher capacity and also guaranteed end-to-end reliability levels if you embrace this wireless-friendly TSN scheduling. And just as Janer said, I think 2 days ago we received the very lucky or very fortunate message that IEEE has accepted this project authorization request. And all these concepts are now going to be hopefully standardized under the synonym 802.1 QEE. So 2 times the E. Okay, we're very proud. This is a great result. This is, of course, not only deterministic 6G, but to a large extent, right, the initialization of this has been coming out of deterministic 6G. So moving a little bit forward, we also worked on time synchronization, for the cyber-physical systems, cyber-physical continuum, time synchronization along the entire application path, but then also the elements within the network infrastructure is very important, is fundamental. And in time synchronization systems, it's a known problem or challenge was that when grandmaster clocks are actually failing, that there are certain types of distributed approaches, how to recreate then a new grandmaster clock, but with quite some costs in the transitioning. And this is something we were not satisfied with, so we worked out a new approach that then also ended up in a new amendment where it was about a hot standby grandmaster clock, such that in case of a failure or a loss of the primary clock, the backup clock in the system could be recovered extremely fast, and we had to work out new architectures for that. So this was also a very good result that we achieved among many. And then finally, I also want to put your attention here on tooling. Tooling is something that oftentimes or sometimes is a little bit forgotten, or it's just taken for granted. But deterministic 6G had the ambition from the beginning to also make a contribution towards the community to improve network performance tools with respect to these central aspects that we were seeing and that are challenging us. And here we were able to establish a new 6G DETCOM simulation model that essentially can take packet delay variations, and then we can plug this simulation model, which then emulates a wireless TSN bridge with whatever delay variations you're interested in, with different type of then also scheduling approaches. We can plug that into a given TSN simulation environment for a much better and much more accurate evaluation of, on the one hand side, 5G or 6G performance behavior, prediction accuracy, and then also different scheduling approaches. Okay, now these were just a couple of snapshots. We had many more results. And this is kind of like a non-exhaustive list of the additional results. Some of them are also going to be presented here during the sessions. Some of them are represented here in the demos. What I want to say is, as János also mentioned it, apart from all these technical results, right, it's also always the people that are involved. And there I think Deterministic 6G did really a good job, not only in creating a very active project itself, but also in reaching out through workshops, through dissemination events like today. So we're looking very much into the, we're looking positively into the future. Concluding, so we had a set of significant achievements, and we will see much more of them in detail over the next couple of hours. You can, of course, ask the question, so what is missing? And what is missing is perhaps extensions or further deeper investigations on some of the entry points that we found. One is for sure even tighter integration of wireless-friendly TSN and 5G, 6G networks. Also on the machine learning prediction frameworks, the scope can be extended. And then we also think that co-design of systems, which is something we had not been emphasizing very much in Deterministic 6G, and weaving it together with what is called goal-oriented communications is a promising direction for the future. So, thank you for your attention, and with that, I'm now passing on. Or am I staying here? How do we run it? Do we take questions now, or do you take questions after Stefan? Stefan is already lining up. Now, okay, excellent, good. Do we have any questions? Do we have any questions online? Nothing online, okay. Yes, please.
Security properties of this.
Yes. Well, in the project, we of course considered security. In the original definition, we were coming from automation systems, which oftentimes operate in closed environments. But let's say, in a scalable system, security is very, very important, and therefore, this is also something that needs to be worked on more in the future. Good.
Okay.
I think maybe then we just move on.
Yeah. We can move on. Thanks,
Okay.
James.
Thank you.
Yeah. And next speaker, Stefan Parkvall from Ericsson, about 6G wireless connectivity. So, please.
Thank you. So I will talk about 6G more in a general sense, a little bit where we are from a standardization perspective, where we're heading. I think the first question is, what is 6G? You have it in your project name. And I'm pretty sure you have as many definitions of 6G as there are people in the room. So I think if you look a little bit at what's happening, I mean, this is far from a complete list, but we have monetization and these type of things, exposure. We have automation, we have the cloud aspects, and we have the network evolution, etc. And all that is a continuous evolution that's ongoing now, from 5G to better and better things. So one aspect of 6 would be to say, okay, let's take everything we have in 2030, all these areas together, whatever that is 60. Yeah, sure. That's one definition of 60. Or you can be, I wouldn't say more narrow-minded, but you can zoom in a little bit more on the RAN side and say, okay, whatever we have on the RAN and maybe core in that time frame, that is 60. That's another view of 60. I'm not saying that one is better than the other, but different people put different things in this word 60. So that's something to be aware of. And since I'm a RAN guy, I will focus on the lower corner here, that definition of 60. That's my take in this talk. But sure, there are other views as well. That said, the 60 standardization has started. So we are now moving away from this more kind of visionary research into the first standards of 60. There will, of course, still be research, there will still be implementation, there will still be things put into the 60 networks for many, many years. But the standardization has started. So we had, at the bottom here, you see a picture from the kickoff workshop in spring in Seoul, in Korea. And then we had the first working group meetings in India 2 weeks ago. So now the actual specifications are started to be not yet written, but the work for that is ongoing. So. And it's a kind of two-phase approach. There will be a stud item running until first half of 27, followed by a work item where we actually do the hard decisions. And the target is to have ready specifications by the end of 28 or early 29, thereabout. It's not 100% defined exactly when it will be done, but in that range. And then probably some commercial networks starting to appear in 2030 and onwards. So that's a little bit planned. So the 60 standardization has started. Not like we had like 5 years ago when it was more kind of visionary research. Now it's actually things are happening. So what do we want to achieve? What do we want to do with this 60 system? And I actually start with this slide this time. I usually do it in a little bit different orders, varies, but I think the scalability is something that in some sense is new to this Radio SX technology. In the past, we have focused a lot on let's do an MBB system, and then after a couple of releases, we figured out, we probably should do some IoT stuff as well and some other things. And then we have modified the standards of that. But what if we start from the other end and say that what is the lowest, simplest type of device that we want to support? And make sure that we have all the tools in the standard from day one for that device. And then we can scale up to more advanced things. So that has some impact on smallest bandwidth you can run in, what type of random access procedures and these type of things, how you design those. So the idea here is to make sure that the lowest end 60 device is capable of doing some kind of IoT type of applications, replacing the LTM and narrowband IoT that we have today, so that we can move on from 4G technologies for IoT into the 60 era. And of course, these devices have very, very long cycle time delivered for 20 years or so. So the narrowband IoT devices, they will be in the networks until 2040 something, for sure, because operators offer very long-term contracts. But starting from 2030, they can start to offer 60 contracts for IoT. That's a little bit the idea. Then a couple of other areas that I think should be thought of. It's far from complete here. Fixed wireless access may sound boring, but it's actually a large part of the traffic in the networks for some operators. So can we do something more to improve that, make it even better than what we have today? Maybe it comes to more MIMO layers in the uplink, etc. I don't think there's a lot you need to do in the standard, but there could be things that we need to think about. Satellites. I think people in general would like to integrate end-to-end in 60. In 5G, it was something that came in a late release. What if we designed the 60 RAT from the beginning so that we have the parameter ranges when it comes to Doppler and delay, etc., so that we can also cover these type of deployments? Again, probably not a lot we need to do technically in the specifications, but if you think about it from the beginning, then we get that into the first generation of products, and it's much, much easier to get it going commercially. Sensing and positioning, everyone talks about that. It's quite a different thing to what we have done in the past. It's not a communication service. It's basically positioning of passive objects. It's a radar-like type of setup. What can we do there, given that we have a lot of base stations and devices and radio equipment out there? Can we sense things? Can we make a picture of our surroundings somehow? And yes, you can do it. Drone tracking has been popular. Can we do more than that? And then also on top of that, the type of business aspects. How can you sell this service? Who's willing to buy it and so on? So that I would say is still an area that is quite a lot of research to be done. It's something new. And then I put in time-critical communication. I thought I need to have something that appeals a little bit more to your project and what you have been doing. And I think that is something that needs to be there from the beginning as well. We have done a little bit in the past. We developed 5G and then we started to add features in later releases. And that's of course good, that can evolve a standard, but it also has the drawback that they come later. They may not be supported by devices, not by all networks, and sometimes 3GPP has a tendency to over-optimize a little bit. So what if we can get some of these things into the first standard in such a way that we can address, let's say, 80% of the use cases or the vast majority of the use cases, maybe except some corner cases, with some simple mainstream technology so that we can get things going commercially. That's a little bit the thinking around whole this slide, that don't start to optimize for a corner case and the solution comes later. Try to make something that you can deploy early on and make sure that it starts to happen commercially. And if it takes off commercially, yeah, sure, then we can start to introduce even more enhancements and features. So that's a little bit the message on this slide. And for sure, it says and more in the corner. There's of course a lot more than just this, but just to give a little bit of feeling. So, what are the key 60 principles from an Ericsson perspective? I think a lot of this is shared by others, but of course companies may have slightly different views. I think a fairly common view that most people agree upon is that 60 should be a standalone architecture only. I think we made a mistake in 5G when we made multiple architecture flavors of 5G. The non-standalone one where you use 4G for initial access and then you start to run 5G, and the standalone. And most operators went for non-standalone, so they're still stuck with the 4G core network. And they miss all this slicing and the real 5G features that we were talking about for many, many years. So let's not repeat that mistake. Go standalone only and avoid this kind of non-standalone things to reduce the number of options and get the new solutions going commercially. On the core network side, we think that 60 should connect to the 5G core or an evolved 5G core. And there's multiple reasons for that. One is that the 5G core is designed in a very flexible way. It's cloud-friendly, software-oriented, etc. So it's very easy to plug in new modules for whatever new things you need to do in that core network architecture. The other aspect comes back to this non-standalone thing. Since operators are just about to migrate to standalone, some of them have done it, a lot of operators are still on the 4G core. Coming to them and ask them to throw out your 5G net core and put in a 60 instead 2 years later, it's not really that attractive financially. So that's also an aspect to keep in mind, that if operators are just about to migrate to 5G core, maybe we should build on that, since it actually can solve the technical things we want to solve. We say that it should be an intent-based and programmable network. That, of course, sounds a little bit like buzzwords, and it is. But with intent-based, that really connects back to this automation thing I had on one of the first slides. Instead of configuring a lot of parameters in the network, thousands and thousands of parameters, that is really difficult to have a grip on what they do. If instead can lift the configuration to a higher level, just give an intent to the network. In some way telling the network, yes, I would like to run this IoT service with at most 50 milliseconds packet delay. Can you set that up for me without affecting my mobile broadband users? And then some AI machine or something figures out how to do that, tunes the network, tracks what's going on, adjusts so to fulfill that intent and tells you back that, yeah, I did this and this because of. If you can do that, then you can actually start to guarantee services. And you can start to offer new type of the services from the operators to customers. So then you can broaden your customer base or applications from what you do today. I mean, basically what an operator sells today is best effort. And they've been doing that for the last 20 years. So maybe we should try to move in a more direction that you can actually offer service that gives you some guarantee. Within this city, yes, you will get 10 megabits per second. I guarantee that with at most this latency. And then you can start to invent new services. We said that it should include open interfaces. And I think, yeah, we've had that in the past as well. So, I mean, the RAN core interface, that's an open multi-vendor interface. You can buy the core from one vendor and RAN from another. Of course, also between the mobile and the base station, that's also an open interface for obvious reasons. But we would actually also like to open up the interface between the radio and the rest of the base station. This lower layer split, as it's called. It's currently defined in ORAN. It's another organization outside of 3PP. But that interface is something we would like to open up so that you can buy the radio from one vendor and the rest of the baseband and scheduling, etc., from another vendor and just connect them. That's also a big push from operators. They would like to go in that direction to avoid various types of lock-in effects, etc. So that is something we would like to open up that has not been open traditionally. Spectrum-wise, of course, we should be able to run in all existing spectrum and as well as any new spectrum. There we have the problem, though, that there is not that much new spectrum available. So in some sense, this is maybe the first G where we don't have any new spectrum. Previous Gs, there have already been a new frequency band opening up, and great. 60, it might be a little bit different. There could be some spectrum coming in the centimeter wave range, 7 to 15 gigahertz. Probably most in the lower part of that, around 7, 8 gigahertz. So yes, maybe a little bit of new spectrum there, but otherwise, we really have to run on whatever frequencies we have for 5G. And that means that we need to coexist with 5G in a very, very efficient way. We can't go to an operator and say, yeah, throw out your 5G network, put in a 60 one. That won't fly because they have a lot of 5G users out there. So we need to be able to put the 60 carrier on top of a 5G carrier and very, very dynamically share these resources between the two Gs, basically on a millisecond time scale as part of the scheduling. So whether we schedule a 5G device or a 60 device should be no difference. That should be a very, very rapid mechanism. Fortunately, that is relatively easy to do, since 5G was designed in a very, very lean manner with a very few always-on signals, etc. So it's doable. But I would say that is a must. If you come with a 60 technology that cannot share spectrum with 5G, you're doomed. This is really a must for operators. And of course, new use cases and etc. in a cost-efficient manner. Then a slide about little bit the Ericsson approach to 60, a little bit of a keep, change, add paradigm. And the idea here is that let's keep things that work well in 5G. No need to reinvent the wheel. And one obvious example is the OFDM waveform. It has served us well both in 4G and 5G. We don't see any other waveform that is significantly better. So why change? Why spend beating time on discussing that? So keep OFDM, that also make this spectrum sharing much simpler. You can make a similar thing around coding, channel coding. Channel coding guys, they usually fight for 0.1 dB gain. Sure, nice, but will it make a big difference in the system? Maybe not. So if you don't see any major advances in that area, we can equally well use what we have in 5G for that and spend the efforts on other areas. For example, things that we would like to change in 5G, design decisions that were less good. And one example is if we go deep down into all the scheduling mechanism in 5G, you will find out that, yeah, there are a lot of restrictions what you can do because the device needs to have some simplicity, can't do anything. fine, they all look good in isolation. When you put them together, you find, okay, this was quite serious scheduling restrictions. I can't schedule packets out of order. If I request a CSI report, which takes quite some time to deliver, yeah, then I can send an uplink data in the meantime and things like that. So here's an area where we actually see improvement or quite a big potential for improvements if we rethink a little bit around the control signaling and the scheduling framework. So that's something we would like to change. So that would be good to discuss in 3PP and modify. Some unified mobility is another area on that. And then we have the add category. Things that we would like to add. New services, new use cases. I think sensing is an obvious thing. Something we don't do in 5G. So let's add that. Resilient communication is another area where I think we can add mechanisms that we haven't had in current generations. For example, if the UE starts to detect that something strange is going on, the base station is about to fail, for example, maybe you can autonomously trigger and hand over to another frequency, another base station. These type of mechanisms. So a little bit keep, change, add. And the idea there is to spend the standardization and working what we work on new things that actually bring big benefits instead of just reinventing the wheel. Spectrum sharing, I think I already covered this, so I can go quickly with this. I mean, absolutely essential to have a 4G, 5G sharing in a dynamic way. It's a must. And I think that's a common view in the industry. Then we also need to, in some of the new bands, unfortunately the 7 to 8 range is not completely free. We may need to share with other technologies like satellites, radars, fixed links, etc. So then we need to find ways of coexisting there to really get access to this new spectrum. I think this is probably obvious for you guys, you since you work with delivering packets, but there is still a tendency in general in standardization and academia to look a lot on full buffer. You have an infinite amount of data to deliver, and then you start to optimize your MIMO scheme or whatever it could be, and after a while it converts to some nice solution. Problem is, most packets are small. So if the data is gone before all your nice bells and whistles are up and running, they're not useful. So don't forget these type of things to rapidly get up and running. Camp on the right carrier, activation of new carriers in a very fast way, and things like that. So don't forget the small packets. That is a general message here. Then, of course, we need to do good things for large packs as well, because they few large packers actually is most of the data volume, but don't forget the small ones. And this one, I don't have time to go through all of it. I think I mentioned some of it. It's just a smorgasbord of technology areas that will be worked upon in 3DPP. Energy performance, for example, operators are really keen on reducing the energy consumption in the networks. That is one of the big parts of the cost of running the network. So can we reduce energy consumption on the base station side without messing up the performance? That is something we should do. Uplink, downlink, decoupling, that's just based on the, in some sense, very simple observation that the best frequency band for downlink traffic is not necessarily the best frequency band for uplink. Maybe you want to run your downlink in, let's say, 3.5 gigahertz, a lot of bandwidth, you have a high power base station, but maybe the uplink should be, for some users, in a low frequency band, 700 meg, because you don't have a lot of power in the UE, so you need to use a more propagation-friendly frequency, so to say. So a little bit more free combination of uplink and downlink. I think I talked about scheduling and sensing. AI/ML, nowadays you can't have a slide without having that word somewhere. It will play a big role in the future, for example, for automation and these type of things. I think AI primarily is for problems that are poorly modeled, where you don't have a nice theoretical foundation. Problems that are multidimensional and nonlinear. So probably a lot of RM problems, like handover decisions, when to activate a new cell, these type of things. Probably less when it comes to well-defined layer 1 problems like channel coding, for example, and things like that. Could be some aspects to do in channel estimation. Positioning is an area where we're seeing quite good gains from AI as well. Most of these things are implementation. I mean, nothing tells you how to implement your receiver, your algorithms. If AI makes sense, put that in. There will be some mechanism when it comes to observability and data collection that we need standardized though. If you look careful on that figure, you see I have an AI in the base station and AI in the UE. There is a discussion, and that's easy because then I can pretty much build whatever I want in the base station, and same thing on the UE side. There are ideas on an AI mod that spans both the network and the device. But then you have a big open question, how to standardize that? Because we don't want to risk interoperability between devices and base stations. That has been the key to the success of cellular networks, that any brand of a device can communicate with any brand of the base station. So no matter if you have Samsung or an iPhone, you can still talk to an Ericsson base station or a Nokia base station. But if you start to have AI model that spans both of these nodes, how do you standardize them so that you still have that interoperability? And I think that's an open question. So that's something we, at the moment, are a little bit careful with or reluctant to, because this interoperability is super important. And I think I talked about the other boxes to some extent. And again, ... This is an incomplete list. There's more you can add to it. Put in whatever favorite technology you have in mind, and that could potentially fit there. Last slide, or second last slide, just to give you some performance numbers. This is a slide that we typically use with C-level people, so it is very high up there. They don't understand all the underlying simulations, etc. But it's basically to show that, yes, there is potential with 60 compared to 5G, technology potential. So energy efficiency, for example. In an unloaded network, if we can cut down the amount of always-on transmissions, we have very few of them in 5G, but still there are some synchronization signals that go out every 20 milliseconds. If you can expand that to go out every 160 milliseconds instead, yeah, you can save 77% of your energy in an unloaded network. Plus 56% in data rates. That goes back to the scheduling constraints that I talked about. If we can remove them and do something there, we can see quite big gains. And this is probably something that academia doesn't look into, because they don't go deep into the implementation details of the scheduler. But there is quite some potential there. 10 times uplink improvement. Yeah, we can get that high improvement sometimes by using different frequency band for uplink and downlink, by decoupling them. What else? Yeah, positioning accuracy we have there, and 200% increase in downlink capacity. Yeah, that comes from if you get access to more centimeter wave spectrum. Yeah, and of course, I mean, it's a no-brainer that more spectrum gives you higher capacity. But the interesting thing here is that you can actually show that these 7 gigahertz frequencies, centimeter wave, can be deployed on the same site grid as current midband, the grid that operators have for 3.5. And still get the same coverage. So that's the message here. So there is quite some potential in 60. That's the message here. Okay, so to conclude, standardization has started. We're up and running with all the contributions from companies, all that, the discussion in the same way as usual. I talked a little bit about the main principles. I think the standalone one is probably one of the most important one. And that we do the spectrum sharing between 5G and 60, the keep, change, add type of thinking. And then, yes, there is a lot of our performance potential in 60 if you do it the right way. So yes, there is a reason to move on to 60 networks in the future to get that. Then, of course, we should make sure that we get all this dependable communication, the time-critical communication, etc., into the standard from the beginning, so that we really get it up and running as well. That's it. I think I was perfectly on time looking at that watch. Questions, comments, or are you in a hurry for a coffee break? I will hang around during the coffee break as well. So, yeah.
Yes, Stefan. Thanks a lot for this very interesting talk and the overview. How within Ericsson, also within standardization now, the activities are shaping up. I would like to come back to the context of deterministic 6G. Of course, what you have been addressing here is highly, let's say, RAN-centric, and I think you also made that point at the beginning. If you look at, let's say, everything in the box dependable communication, it's of course the RAN, but it is then also the integration with the core, potentially with compute elements, and then also the working towards applications. So for folks that are interested in working on this and taking now the specific RAN perspective, what would you think are perhaps the most important challenges that you see to address something that could be on the market in 4 to 5 years, not in 10?
I think it's difficult. I don't have a favorite technology topic to answer that question, because I haven't gotten exactly that question in the past. But I think it's a good one. But I think what we should avoid is a little bit, if you look on the URLLC work in 5G, that was very, very RAN-centric. People just looking at the radio, discussing whether we can shave off a millisecond here, optimizing something, ended up with something quite complex. And completely forgot about the core network, transport network, and everything else in the network, which is where you waste time in some sense. Where you shave off a millisecond or so in the air interface is not a big difference. But if you can take away a couple of milliseconds in some core processing or some transport, yeah, then you start to get bigger gains. So I think what we should do is to lift our view a little bit, to take a little bit more holistic perspective. And I think that's what you try to do in the Deterministic 60. And I think that's good. And I think that needs to be in the mindset of people when they start to work here, so that they don't go deeply down into some detail that are their favorite and get that into the standard and messes up things. And I think we've seen that ourselves as well when we simulated just normal broadband traffic. The interaction between uplink and downlink, TCP protocols, and these type of things are super important. You can't just look at one direction and forgetting about the other one, because improvements in the uplink can give you quite big gains in the downlink and vice versa. So I would expect that would hold for deterministic things as well. If I just work on one link and forget about the other link, yeah. So lift the view a little bit, take a little bit more holistic view, and put your ideas into perspective. I think that's important to do. Yep.
Thank you, Stefan. A question on, I mean, we're coming here from a research project which has just come to an end, but there are new research projects starting and others are still ongoing. And I think so, as we have just concluded our projects, I think the insights that can come out are now at the right time for being taken as inspirations for standardization. Is there anything that is reusable? What do you see is the potential for having impact on the standard for projects that are starting up or that are ongoing? So what maturity level do you need to, I mean, you cannot come with a wild idea in a standard if it hasn't been proven or so. So what do you think is the impact of open research collaborations that we have in these collaborative projects of still impacting the standard? On what level and where are better opportunities and less opportunities?
I think in general, academic research projects should not work too close to the standard time-wise. So if you start a new research project now, I think either you should look on things that you can implement based on whatever standard we have, or you should look a little bit more like 10 years into the future. I think it's been a little bit unfortunate, and it's probably due to the funding structure, that a lot of research is too short-sighted. They're basically looking at the next release in 3DPP, and there's no chance that university will come with their idea and get that into the standard with all the big companies having their discussion and their views. So either look on more things, what can you implement based on the current standard or with a small modification of it, or look further into the future, like 10 years down the road. So, I mean, in some sense, academic research, there should be kind of 7G type of mindset to some extent, if you're more standard-oriented things. So I think that's usually what I say. Sure, it's good to understand what's happening in 3DPP and know a little bit about boundaries, but don't feel restricted by that. Broaden your view and either go further into the future or look more in the application domain or implementation domain, so to say.
questions? Okay, if no. There is one question from the online audience. How does integrated communication and sensing integrate into 6G? Any ideas on interface aspects and timeline?
Yeah, I think this ISAC, integrated sensing communication, is a very popular topic for many reasons. And I think the starting point is, I mean, for it to make sense, you need to reuse the sites, the frequency bands, and the radio hardware. Maybe with very, very small things. If you come with a sensing thing and say that, yes, I need 100 gigahertz and a super dense deployment, then it's something completely different. Then you're probably better off in a radar conference or something like that. So you have to reuse the sites and the frequency bands, because the idea is to basically piggyback on something that you already put out there in order to reduce cost. Once you've done that, then I think what we probably will see in the first sensing is some form of a reference signal or some ping that you can send out and then listen to the reflection and do some radar processing. And that is relatively easy to introduce on the lower radio levels. And what we have seen is that the OFDM waveform, etc., is just fine. Then there will be some standardization work on the more architecture side. What processing of this radio reflection do you do in the base station? What data do you send up to some more kind of central collection box? And what type of data do you then expose to the customer? Because I think that is still an open question. We know to some extent what we technically can sense and do. There's still more work to do there. But then we have all the more kind of business aspect to it. Who is willing to pay for it, etc. And it seems that drone detection, which probably is a relatively easy problem with no clutter and the drones in the sky. So that's technically a little bit easier problem, and there seems to be some business interest in some countries around that as well. Use cases like sensing people walking on the street is probably further into the future if you can do it. It's quite tough with all the clutter, and what type of service do you do out of that? So that I think is a little bit more open. I don't know whether that answered the question, but at least I talked around integrated sensing and communication for a while. Yeah, one question in the back.
Thank you very much for the talk. It was very interesting. And I've seen that you mentioned before that one of the area which 6G aims to address is the integration of AI and machine learning. And I would ask you, what do you think about this? Like, in which direction is the standard moving regarding this? And especially, why and how these networks can benefit from standardization of the 6G or the new 6G standard? What is the relationship between the integration of AI and machine learning and the 6G, and how they can benefit from this new standard?
I think, I mean, AI and ML is already happening in 5G. There is parts of that in the Ericsson products already. So you can do a lot on the implementation side. As I said, these type of complex RM type of problems is probably a prime area where you can do things. That you don't need to standardize to a large extent. But what you probably need to standardize is some observability or data collection. I mean, if you want to run your AI algorithm here, you probably need a lot of measurements, signal strength, quality, whatever it could be that you need to feed into your AI algorithms. So I think those measurements needs to be standardized. And they are not really there in 60. So there I think we will see a lot. There will probably also be some standardization around some life cycle management type of framework. I mean, how do you start an AI model and how do you replace it with a new one? These type of things. So that could also be something that shows up in standard. But to a large extent, observations and data collection. There has been quite some work on the radio side, on the RAN side in 5G on AI in release 18 and 19, and around beam management, positioning, and CSI report, and these type of things. I think the biggest potential what we have seen is in the positioning domain. There you can really get large gains because positioning with all non-linear salp propagation is quite a tricky problem. CSI reporting, yeah, we have seen some gains there. So that's probably something that will happen in 6G as well, that we make these type of CSI code books, etc., more kind of AI-oriented. Things like channel estimation, these type of things, that I would say is more implementation aspects that you don't need to standardize. Other than you standardize requirements that you need to be at least this good, but how we get there, that's up to you. Yep, 2 questions over here, I think.
Considering opening up the standard between the radio and RAN, and let's say 5G network being a smaller size network in number of radio and opening up, do you envision that all the specific hardware requirement or uniqueness that Ericsson, Nokia, Huawei had will disappear and you will all be using off-the-shelf components? So not developing your own ASICs, not developing it will be kind of off the shelf because of the volumes and this standard openness.
No, I don't think so, and I don't hope so. So I think, I mean, of course, it will put pressure on us as a company to deliver good radio. And to do that, we need our own ASICs to do multi-antenna processing, etc., etc. So no, I don't think so. But of course, the competition will be there, which is, I guess, also good for us. I mean, we need to keep on our toes. And the same thing on the baseband side. I mean, we need to be good there as well. But I think this opening up, it is a good thing, both from operators and the industry as such. And it is an interface that is relatively well defined. You can open it up, and it doesn't have. Yeah, sure, you need to test it and integrate it, but that is quite okay to do compared to, for example, the F1 interface between the CU and DU that we have in 5G, which it's not a multi-vendor interface. No one is deploying it in multi-vendor fashion, but it causes a lot of complications because some decisions are in the CU, some in the DU, and you need to exchange it. So that is an example of a bad open interface that is not even open. But I think this radio interface is relatively easy to open up. And yeah, sure, it will be competition, but we need to be good. I think there was one more question here in the front row.
My question is about dependable communication. What is the objective for you to ensure dependable communication? Because maybe it's not enough to ensure that the system will continue to work even in the presence of attacks. Do you understand my question?
Yeah, I think I understand it to some extent. It's more than just handling outages, and I agree to that. But isn't it coming back to what I talked about in the beginning about intent-based management? It's also related to that. If you can sell some guaranteed service level, then you can start to invent applications with that assumption. I mean, remote controlled cars or something like that. It's not good enough if you have coverage in most of it and typically it works. No, you need to be guaranteed that they have connection and some reasonable latency. Yeah, then I can remote control the car in this area. So I think it can trigger new types of business opportunities and business cases as well. I don't know whether that answered your question, but otherwise come back in the coffee break. Yep.
You mentioned also we need to start from like low level or in the bottom like red cap or narrowband IoT or so on. But how we want to ensure the ecosystem is ready, like the chip maker for the user side?
Yeah, it's a good point. And I think that there are 2 aspects to this starting at bottom. One is to make sure that the standard starts in the bottom. So that let's say that we agree that we should support anything from 3 megahertz and upwards in channel bandwidth, and we design our initial access with that assumption, and that we should work with one receive antenna, whatever it could be. So that is, the standard needs to be ready day one. That doesn't necessarily mean that the chipset will be there day one. They will probably come when the market is there commercially. So they could come a couple of years later. But the nice thing is that once they show up, they're immediately compatible with the first base stations out there. So they can access the existing network instead of, yeah, you don't have chipsets, you don't have network, where do I start? Which was a little bit the situation with narrowband IoT and these type of things. And it can also, it's really a way of taking IoT from kind of 4G technologies. Narrowband IoT and LTM is 4G based into the 6G era. And that has quite some good impact on the power consumption in the base station and the network, for example. There's been examples of operators that run 5G and then they want to turn on narrowband IoT and suddenly, poof, the power consumption went up like 15% or so. Just because the way that narrowband IoT technology and LTM technology was designed. You can't really sleep with your base station. But to come back to your question, I think one should think about the specification and the commercial availability a little bit separately. It's important to make sure that the specification supports this from day one, and then the commercial availability that comes when there's a market for it.
Okay, then thank you very much, Stefan, and thank you, James. I guess this is the time for coffee break. But we can, of course, continue the discussion.
Yeah, I will be around in the coffee break, so feel free to ask questions.
And one important information, so if you want to go or if you want to leave the room, please use the card. So I guess if you open the door without the card, the alarm signal will be activated. So we should avoid that option.
That's a way to lock in your audience. No one can
Yeah.
escape.
Or you can ask an Ericsson colleague to assist.
What do you use for sending the alarm? 2G? 2G? Like in the elevators?